Okay, let's start the afternoon session. Just one talk by Noel from Duke University and telling us about peptides.
All right, thanks, Matthew. All right, so I apologize if I need to take frequent water breaks. It's very dry here. When I left North Carolina, it was the same temperature, but 85% humidity. So I'm a little dried out. I apologize for that. But yeah, so I am from Duke. I trap ions. I'm an experimentalist. So especially this lecture is going to be very experimental. And yeah, let's just get started. Okay, so this is my current plan for the lectures this week. I reserve the right to change this at any time. I'm going to start with ion trapping 101, and in particular, tell you how to trap an ion. So give you a couple of examples of ion qubits, and then hopefully today I'll have time to do some light matter interaction with single ions. And then next time we'll jump into the many ion case and how we do 2 qubit gates. And then the third lecture, I think I'm going to talk more broadly about kind of the ion architecture and where it's going. And then maybe talk about magic. Okay. So references for this lecture, mainly I'll point you to this last one. So Chris Monroe has some awesome resources on his website, which is where everything I'm going to present to you is based on. So you'll find references on all of this there. Okay, so this kind of came up earlier, so I wanted to just touch on it a little bit as the experimentalists in a room full of mostly theorists. So why talk in this much detail about hardware, right? And I think it's important for several reasons that everyone learn a little bit more about the hardware that we're actually using. The first is that the error mechanisms matter. So you kind of got a flavor of that from Zlatko earlier, right? There's coherent error, and there's incoherent error, there's spam. And depending which one you're trying to deal with, you need a different strategy, right? And this is different from one platform to the next. So it's important that you understand the particular mechanisms of the platform that you're working with. The second point is that co-design is faster. So you have an application in mind that you want to implement on a quantum computer. If you work closely with the hardware, you're going to get to a result a lot faster than if you just assume some abstract model. I have universal computation. Okay. And then on that note, we are far from fault tolerance. We have these noisy systems, and they're getting big enough that it's annoying to simulate on your laptop. So let's do something with them before we get all the way to fault tolerance, because there's going to be a number of years in between those two things. And then to the point earlier about having fun too, I think the more you know about the hardware, this knowledge is power, and you can do things like co-design and move forward in the field and have more fun with the quantum computers that are out there. Okay, so we're going to start from the very beginning. How do we actually trap ions? And so this is going to be entirely electrostatics and some, pretty much a harmonic oscillator. Everything's a harmonic oscillator. Great. Okay. So first we start with the most basic thing. We've got a charged particle, and we can't create a trap in 3D due to Laplace's equation, right? We can't just make a trap in 3D using static charges. Okay. So we have to come up with tricks to get around this. And so one of those tricks is to apply a strong magnetic field. And so this confines the ion or the charged particle in a 2D plane. And so what the ion will do is in that plane, because it has this Lorentz force pushing it around, is it will make trajectories like this in space. So that's one way to do it, and that's called a penning trap. And then you can just put electrodes on top and bottom to confine it in that last 1D direction. And you can fit many, many ions in these types of traps. Here's an example. So this is beryllium ions in a penning trap just up the road at NIST. And there are ways you can kind of deal with this complicated motion. And actually there's a lot of interesting recent directions with penning traps. But by and large, the ion trap technology that you'll see out there today is based on a Paul trap. And so I'm going to go into more detail on exactly how those work. Okay, so I'm going to start with this configuration of electrodes. So I have 2 ground electrodes and 2 electrodes that are a positive voltage, and my field lines look like this. And what I have is a saddle point. So I have confinement along one axis, but anti-confinement along the other axis. Now, if I switch to negative voltage, my field lines are reversed, and so is my saddle, and I've switched which axis has the confinement. Now, from the point of view of a particle right in the middle of that saddle point, what I can do is oscillate between these 2 configurations. And I wish I had the animation, but it looks like the saddle is kind of like flapping up and down, right? And so on average, a particle in the middle is going to see a harmonic oscillator potential. So as long as you can kind of do this oscillation faster than it's moving out of that null point in the middle, this is a very, very good approximation. And that's the trick of a Paul trap. So now instead of using static voltages, we have one that is oscillating. And a simple version of that, so this, I've been talking about kind of this 2D plane, but you can extend it into 3D in this direction with rods like this. And depending on the phase of your oscillating voltage, you have a saddle in one direction or the other. And so the solutions to the, yep. Sorry, can you speak up a little bit? Well, they kind of do, right? So on average, oh, I see what you're saying. Like, why is it not like the other way? Because the particle is positive. So I think if you put a negative, no, that's not true either.
Motion and acceleration is 180 degrees out of phase. So when you are repelled, you repel left. You are attracted.
Okay, so we have our harmonic oscillator, and it turns out, well, before we even turn it into a harmonic oscillator, with this oscillating potential, what we have is the Matthew equation. And so we write this down where this phi naught, this term out in front, is going to be some DC term plus this oscillating term, which has some amplitude and some frequency of oscillation, omega RF. And then I can write this down in 3 dimensions, and I just have a different coefficient on each term. And I could kind of tune these based on how I build my trap. And the solutions to this, the equations of motion and such a potential for a charged particle, are simply solutions to the Matthew equation. And so this is the Matthew equation here. So I have these 2 parameters here, the A and the Q parameter, that determine whether these solutions are stable or not. And so I think that actually maybe comes back to the earlier question, right? So if these A and Q parameters, well, we'll come back to those, and I think that will answer your question from earlier. Right, so they're determined by just the properties of this potential that we're applying in this particular way. So we have the charge of the particle we're trying to trap, the DC voltage you apply. This alpha is something you can change. You could scale it up and down. We have the mass of that particle. This R naught is kind of a characteristic distance from the center of the trap to these electrodes here. So it would be from the center to one of these rods. And then we have this frequency that we're doing this oscillation, this omega RF. Mm-hmm.
What you said before, if you don't oscillate alpha and beta opposite signs, and Z is roughly roughly zero.
Well, so because we have to satisfy like that the second derivative is 0, right? So if I did that and I had all alpha, beta, gamma, I could not find a solution in which that were true in 3D. So it just like doesn't work unless you have this oscillating, unless you play some sort of trick. And so
I guess what I'm asking, the very first statement you made, like you don't have a confining potential with electrostatic. That's just a statement. DRF is 0, there's no oscillation.
right.
Then it's you know, that's an alpha is positive and beta is negative.
Right,
So
but
not in one direction. Confining in one direction, deconfining in the other.
Yes.
That's the thing.
yes,
And now you have this RF to make them both confining.
yes. So now alpha and beta can be both confining, exactly.
What's interesting, there's no, I don't know where beta enters. Like an A and
So I'm only taking one direction, X. Yeah, this is just one direction. So there are same equations in the other direction as well. Right, no. Yeah. So this is confinement in this 2D plane, which in this case is the XY plane. So there's exactly the same equations for Y as well. Is there a hand? Yeah. Is tau the same as T? No. It's some like scaled time so that it makes this look nice. Yeah. Okay. Okay, and then this is coming back to this idea. So when does this work, right? So when do we actually get confinement instead of anti-confinement? We have to have these stable solutions where the A and Q parameters generally we work in this region here are very small. And then the particle is trapped rather than escaping from this potential. Okay, so in order to do that, we have to tune all these parameters. So generally you pick an ion, so your charge and your mass are kind of fixed. And then you have to choose kind of a size of the trap itself. So how close are those rods physically? And then find a omega RF that creates a stable solution. And then you can also kind of tune this alpha a little bit as well. Okay, so right, so then we can look at the solutions to the Matthew equation, which are essentially, if you look just at this first term, right, it's a harmonic oscillator. Great. And then there's this extra term that's oscillating at this RF frequency. But if we're in this regime where Q is small, we can ignore this. Ignore it. It's always there. It's something we can measure. But for all intents and purposes, it's going to be small enough that we can ignore it. And so what we have is a trapped particle in a harmonic oscillator potential. And this frequency along this particular axis is just determined by these A and Q parameters, some combination of those same exact parameters from the last slide. And so we have our favorite quantum harmonic oscillator. And so this in ions is a very good approximation of the motion. So we can use this kind of pretty freely as long as we keep the ions cold and near the center of the trap.
Is it true just even by symmetry, the confining one gets more confining, let's say X direction, but the Y gets confining, you can get a confining regime, but it's always an isotropic.
No, you can make it degenerate essentially in X and Y. It's not, I wouldn't do that because you're going to make your life difficult. But yeah, if you could make a perfectly symmetric trap, which we can get pretty close, they would be degenerate. There's nothing preventing that in any of this. Yeah. But usually there's some asymmetry. No, the strength of it doesn't matter, the strength of the drive. It's a property, right, of this, let's see, like alpha and beta, right?
You start out with them being the opposite side. Now you add some time average positive shift to both of them. So unless you add a large positive shift, one starts out positive, the other one starts out negative.
We're not adding a shift. I'm trying to figure out how you got to adding a shift.
Static potential that the DC confining one direction, be confined to the other. And then there's a correction, which is the parametric thing, which is a half frequency. X and Y oscillate half frequency, half of omega RF.
Yeah, so the
Big RF and cancels the RF.
so this DC voltage is applied equally on like X and Y, right? So it's just like an offset on everything. I could make it 0 and this would still work. Yeah, but then you still need that third direction of confinement, which is in a minute. But yeah, this is just applying to that 2D XY plane. Okay, so just to give you some physical meaning to some of these parameters, right? So we take the mass of a single ion. We have usually singly charged ions. And then we can make traps that have this characteristic distance of about 100 microns. We apply about 100 volts. And this RF of about 30 megahertz is enough to get trap frequencies in the few megahertz range. And then our A and Q parameters work out that they're small enough and we're in the stable region, trapping region. And none of these parameters are particularly difficult to achieve. Okay, and as I just mentioned, so that was all kind of in the 2D plane. There is that third direction, but we can just put large, positive voltages on either side. So in this picture, this is the Z direction. So the confinement is in the plane that kind of cuts into the slide. And so you can just apply some positive voltages there and you just have another harmonic oscillator in the third direction. Okay. So yeah. Yes. Yeah. So we have different but very similar techniques for cooling. Yeah. Yeah, I'll talk a little about sideband cooling. Yeah, but and Doppler cooling. And I'll talk about like and cool, how does it break, all of these assumptions. Yeah. Okay. So, oh shoot. Sometimes it clicks like 3 times. Okay. Okay, so this trap is a 4-rod trap, so you can't see because they're directly behind these two with these 2 needles. And in size, this is maybe, a few millimeters across. Maybe you think this might be scalable, but I definitely don't think it is. So there's another way to do this that has become the more prominent way to actually create these Paul traps. And that's using surface traps where all of these electrodes are mapped onto a 2D plane. And so the way that works is we take our configuration here. So these are our RF electrodes, and then we have our ground here. And we're just going to move this RF down into the same plane. So now these 3 are in the same plane. And then we take this ground off into infinity. And what we're left with is, I'm just going to yeah, essentially. So now these are all in the same 2D plane. I have my 2 RFs, ground in the middle, and the other ground is kind of off at infinity. And I have a local minimum here in what we call the pseudopotential. So on average, in that oscillating field, I have a potential minimum here. So this is where the ion will be trapped. So this is our 100 microns kind of characteristic distance of this trap. Typically, yeah, it's about 100. And so it's not a perfect, it's not these going to exactly be a perfect harmonic oscillator in all 3 directions. And you can already tell which way the ion would escape, right? It can escape vertically in this direction. But as long as you're cold and you stay close to that potential minimum, this approximation works very well. Okay, and so you can kind of picture it like this. The ion is sort of hovering above the surface. It can pattern electrodes into the surface here using microfabrication techniques, and you can create that third axis of confinement. So we no longer have these large needle electrodes pointing into the trap. We can just use fine control with these electrodes here.
So this must rely on gravity, or it's purely effective.
Gravity is completely ignored here because we have Coulomb forces, which are much stronger. And actually, when we run these traps, generally the ion is actually below the chip. We run them upside down. Okay. Okay, and then this is, an example of how these surface traps can then be scaled up. So in this chip, this is made by Sandia National. Oh, sorry, yeah. Nope, not in this case, no. So right, so at the very center, right, if the ion were exactly in the center at all times, the potential would just be 0. There's nothing there. But of course, it departs from that. And so if you're in this case, it departs in the direction that's confining, it's pushed back down into the potential. On the right, yeah. Oh, yeah, that's the average, yeah. Over time.
You have to, so imagine you solve Newton's equation with the oscillatory multiplication potential with RF. So now your solution is also oscillating. Now you put that solution with its amplitude into the Hamiltonian. Now you have x squared multiplied by oscillatory curve. So that is average to the DCP. And the solution oscillates at half the frequency. X oscillates at half the frequency. I don't quite understand why, but when you square it, then you can't oscillatory.
Yeah, I mean, my very intuitive, of course, feeling of how this goes, right, is the ion leaves in one direction, and by the time it goes very far, the potential has switched to pushing it back towards the middle. So it's always getting pushed back into the middle of the trap. Okay. There's a nice at Duke, we have this little saddle point on a motor that spins in place, and you can kind of put the ball in there, and you can see that on average it's staying right in the middle, but it has a little bit of motion at that frequency that you spin.
We learned about both.
Okay, yeah. Mhm. Okay. Right. Oh, yeah. Yeah, so if you, so we call this micromotion when you're moving at that RF drive frequency, which you're driving the trap. And in general, if you're very cold and you're close to the middle of the trap, this micromotion is very small. But if you are off center, this micromotion can actually heat you in the trap. And so this is something that you can observe in kind of extreme, to us, extreme situations. Yeah. Okay. Good. Okay. So so now we have, okay. So one of the key points here, because this kind of came up at lunch. Let me just go through this. So in this picture where we have kind of the 4 rods, we have the confinement like in this plane along the rods. The RF null in this picture, you have an RF null that extends in a line along those rods right at the center, right? And then I apply some DC fields to make what I'm calling the middle of the trap, right? But technically there's an RF null along that entire length of these rods from the oscillating field. So I can technically trap anywhere along that RF null. And so we use that principle when we make these surface traps, and in this case, the rods, right, the RF electrodes are these big ones that you see running the entire length of the chip. And so what I have is an RF null that runs the entire length of this chip. And then if I so in this case, there are 100 DC electrodes along this chip. I can create a well anywhere along that RF null and have equivalent trapping, as long as I have enough degrees of freedom to control the potential, which with 100 electrodes you do. What I can also do is put more than one ion in a single potential well, and then they're going to spread out along the direction of weakest confinement, which is in this case, again, along this axis of the RF null. Now, if I were to instead apply a DC potential that really pushed them together, they would snap out of this line and begin to break and buckle into those radial directions. And eventually you can actually push until they're completely vertical and even make them swap places. So we have this kind of linear RF null that's determined by this Paul trap geometry here, but we can also make it turn corners, right? So you can imagine you take those rods and you just kind of turn them a little bit. Now I can trap anywhere along kind of that arc that I've just made with those rods. Why not? Because at any given slice, it's just a Paul trap. And as long as I can control the DC fields well enough, then you can do things like move ions around corners. So that's what's great about these surface traps, is we can start to not only just trap a single ion, trap a linear chain, we can start moving them around, swapping them. And in this case, you might notice that these ions are actually equally spaced in the middle. So if they were in a harmonic oscillator, a true quadratic potential, they would be closer together in the middle and then farther apart at the ends. But we can actually just make them equally spaced. We can add higher order terms. We can correct higher order terms. We can do asymmetric things that we want to do for whatever reason. So these traps are incredibly powerful in terms of the control that we have over the ions. And here's just a couple more examples of what you can do. So this came up also at lunch. This is the racetrack trap that I was thinking of from NIST. So this is, I don't even have a year on this, maybe 2010, I don't know. But you can move ions anywhere along this ring here. You can move them down the legs in these directions. And so you can imagine you can start packing in lots of ions into something like this. Your question?
Yeah, so I'm wondering, is it not possible to trap it in all three directions by some different two incumbent commensurate driving or something? Like, why are we restricted to trapping it using this method only in the plane?
As opposed to what?
Like, so it seems like you're trapping it using the power trap in a two-dimensional plane, and then using electrostatic force, you're doing it third direction. So that seems like might not be scalable to beyond 1 year.
Well, so this idea of like what is 1D gets kind of completely broken down when I can just move the ions around at will, right? So like I said, like you can, like in this example, right? We'll get into great detail about how we actually do like entanglement in the ions, but essentially they need to be in the same trap. They need to be like in this picture, these are all in the same potential well, right? But I could put potential wells all over this thing. I have enough control degrees of freedom. And I told you that if I push them hard enough in the axial direction, I can actually swap them physically in place. And then I could move them over to talk to other ions. So that's one thing. Like, so this idea that ions are like 1D connected is just total trash in that model, right? I can do whatever I want. And that's exactly what continuum does. And then I'll talk later about how this chain is not 1D. It's all to all. And I'll talk about exactly how we do that. So when you see these pictures of ion chains and you think, oh, 1D quantum system, no, throw that out the window. I'm going to be able to connect this however I want. Yeah. In a single well versus a single chip are two different answers. So in a single well, in a big enough trap, I can have, say, like 130. But that's maybe good for certain things that you want to do. But then in terms of how many I could fit on a chip, let's say I put 10 in each well, I just need to have enough control electrodes to control all. Say I make 10 wells and then I have 100, right? It just kind of depends on what you can make and control. Mm-hmm. Mm-hmm. Right, yeah, they would just kind of leave along the RF null. Well, they would escape the trap because the like a very shallow one. Yeah, they would, I suppose. Well, then you start to run into issues where this trap is actually longer than the characteristic distance to the surface. And so to create a smooth potential at that long of a distance along the entire, this is like a couple of millimeters, it wouldn't quite work. Right, you could kind of keep them there, but I'm saying they wouldn't be exactly equally spaced because I can't control on that scale exactly, because it would have to be a very smooth harmonic potential over several millimeters, rather than if I keep them. So this scale, these are spaced by a few microns, and that I can do easily. Okay. Okay. Perfect. Okay. So I'm going to talk about two different ion qubits, calcium and ytterbium, particular calcium 40 and ytterbium 171. And these are, with these two, you'll get a flavor of kind of the two types of ion qubits that we have. You'll also find that there are ways that you can kind of combine the techniques of these two ions in a single species. But this will give you a flavor of kind of the operations that we do. Okay, so this is kind of our ion periodic table. So in red, we have ions that have been trapped in these Paul traps and kind of done these sort of quantum control techniques where we're cooling to the ground state and all these nice things. And actually, this is already out of date. Radium has also been trapped. And we choose these atoms because when you remove one electron, you're left with a single valence electron, and they basically look like hydrogen. So that's really nice. We all know hydrogen from quantum 1, right? So we take our harmonic oscillator, we add hydrogen, and we have this beautiful quantum system that we can all understand with just a semester of quantum mechanics, right? Okay, so I'm going to talk about calcium first. And of course, some of these ions are heavier than others as well, which will play into kind of how much voltage you need in order to trap them. And so there are various reasons why you would choose one ion or another. So let's just start with an example of calcium. Well, okay, yeah, so here, this kind of lays it out a little more. So there are I mentioned these two different types, right? So calcium 40 falls into this example where generally we use these optical qubit levels. So just like in hydrogen, we have our S, P, and D levels. This D state is a metastable state, and it's very long-lived. And in the case of calcium, it's about a second. And so I can assign the ground state to be 0 and the excited state to be 1 and make that my qubit. And then you optically access this. So you just tune your laser literally to that splitting, which is in the optical regime. So for calcium, it's going to be about 700 nanometers. And now the other example is so in these species, there's no nuclear spin. However, if you do have a nuclear spin, then you end up with some hyperfine structure. And then you can choose qubits within that hyperfine, within those hyperfine levels. And those have lifetimes that are essentially infinity. So you can think of it like your T1 just is infinite. Oh, that's really nice. This is what they make optical clocks out of, or sorry, atomic clocks. I think, yeah. So, and in this case, these are separated by microwaves. So you can drive them directly with microwaves or indirectly with optical photons. And I'll get more into that. So whether you drive the qubit directly with laser light or indirectly, where they're separated by microwaves. So in calcium, it really is quite the simple of an energy level diagram. So we're going to use a state in the ground state as 0 and an excited state as 1. And this is going to be our qubit. And so I need to be able to manipulate between these states if I'm going to use them as a qubit. And so I've added in a couple of more kind of auxiliary states here that we're going to use for our different operations. So the qubit light is the 729 nanometer light that goes from S to D, the D5 halves. And then I have a couple of what we call repumpers that can get me out of those states. So they have a second lifetime. Sometimes I don't want to spend a whole second, right?
Can you say something about pros and cons of doing microwave optical?
Mm-hmm. Right. So yeah. So this one, obviously, this is a big advantage. But as long as you can work faster than a second, like the optical qubit works not equally well, but essentially in practice just as well. Depends on the species, but yes. So yeah. So what's nice about some of the optical qubits, like calcium, which is what I'm talking about, you could easily get a diode laser at 729, no problem. Whereas, in, yeah, so then, but in this case, right, you can do this with microwaves, but microwaves wavelengths are so long that you can't do any kind of individual addressing with them. So you have to end up using light anyway, but then it ends up being UV, usually with this S to B transition. So there are trade-offs between the two. And then the more recent kind of hot thing to do is use both at the same time. And that's called the OMG scheme. So you use optical, optical, metastable, and ground state qubits. So this would be the optical qubit. Metastable is using states like within these D levels because it is split Zeeman levels. And then the ground state qubit is this ground state qubit here. So you can even combine the benefits of all three. Okay. Yeah, so you can buy diode lasers for all of these wavelengths. So we can manipulate the qubit with this 729. We can do, I'll talk about how we do detection with this 397. And then these are for getting us out of this D state for, say, preparing the state of the qubit into the ground state. Okay, so I'll be a little more precise then about that. So once you have a magnetic field turned on, these states split into the different Zeeman levels, right? So in the ground state, again, there's no nuclear spin in this particular ion. So I just have -1/2 and +1/2. And then in this D5 half state, I have this whole manifold here. And so what I'll do is I'll choose to use this particular level in the ground state and this particular level in the excited state. And I'm going to call those two levels my qubit. And I can spectrally resolve all of these lines, so that's not a problem. Because remember, this is long-lived. So if you take the inverse of a second, you have the line width of this line. So it's actually in like the millihertz range. So you can resolve these. And then I've labeled this OP, so this is optical pumping. So when I want to prepare the state, say in this ground state in 0, I can turn on a laser that takes the ion out of this +1/2, and then repump it into the P state where it then decays down to the ground state. And if I just do this process many, many times, eventually I'm only left with population in the -1/2 state. And so I've prepared my qubit. And that's called optical pumping. Oh, well, okay. Okay, so the other thing we need to be able to do, so we can prepare in this ground state, we need to be able to read out the qubit. And in this case, we use shelving. So if I'm going to use this P state, which has a very short lifetime, 7 nanoseconds. And if my ion is in the D state, or sorry, my ion's in the ground state here, and I turn on this 397 laser that's tuned to the P state, the ion will absorb a photon and then emit a photon, which then I detect on my camera. So this is a picture of an ion. So if I turn on this laser and I see photons coming back on the camera, I know the ion was in the 0, the ground state here. Now, if I turn on this laser and the ion was in the D state, then this is not resonant on anything. So nothing happens. I get no photons, and this picture is just dark. So we're essentially reading out the qubit by looking for bright or dark. And in the case of calcium, there's no pathway it's forbidden that it would decay into this 5/2. And so by doing this, I can cycle this many, many times and just gather lots of statistics and just improve my readout fidelity, not indefinitely, but somewhat indefinitely. So how many 9s do you want? And so this is very high fidelity readout. Okay.
Sorry if it's a
Mhm.
question, but like you're exciting the 397 and it's re-emitting at 397. How do you know like it's fluorescing or maybe you see some reflection from your
So I can also take a picture when I know that there's no ion. And there's no way that I would have any light from an ion. And that's my background. Yeah, that's my background. And we can get that very low. So since the ion is not, it's 100 microns from the surface, as long as the laser beam is not hitting any surfaces, it's just passing through free space. There's no reason that our camera would pick that up. Okay, so that's calcium. And those are kind of the basic atomic operations that we need. To give another example, this is ytterbium-171, which has been a workhorse for a long time for a reason that very, very technical reason that I will mention. So in calcium, it was, you can just get a diode laser at 729. That's great. Okay, so ytterbium, we're going to use a ground state qubit. And in particular, there's a hyperfine splitting in this ground state manifold at 12.6 gigahertz. And these digits are accurate, and I've intentionally included all of them. Ytterbium is used as an atomic clock. We know this frequency very, very well. And then these other transitions, this is kind of similar to that 397. So this is at about 370. So this is what's used for readout. And then we can also get up to this D state level, kind of similar to calcium. And then we have this other repumper here. And what's weird about ytterbium is it has this bracket state, which I won't get into. But you can also use it to your advantage. So I will just mention briefly how we do Doppler cooling, right? So we use this transition here. So again, the P state is very short lifetime. So if you drive from S to P, we'll immediately emit a photon. And so we can do Doppler cooling where we shine in red to tune light. so that when the ion is moving into the laser, it sees it on resonance and emits a photon. And then as long as we have this confining potential on average, this will cool the ion down and take energy out. And so we use this 369 in order to do that. Good questions. Okay. And just an example in ytterbium, so the detection is a little more difficult because of this. We have more than one level here, right? And then we also have this, yeah, it essentially comes from that point. But anyway, so we can still get very high detection fidelity. This is just an example in one of our systems at Duke. And this is just to show you that even if we only detect a fraction of a % of the light that's coming from this ion, we can still get very high detection fidelity. And that's just speaks to the fact that we, this is an atom. We understand its energy levels very well. And so we only need a few photons to make sure that we've got the right state. Okay. So the question before, so why hyperfine qubits? So not only is T1 basically infinitely long, they're also extremely stable in phase. So the T2, this is even misleading, is so long that like we're only limited in our own inadequacies in order to measure it. Okay, that spin is so stable. And so in this example, we're trapping 15 ions and we measure a T2 with microwaves of about 4 seconds. And that's only limited by the stability of our oscillator we're using to do this measurement. We could have gotten better. And so now actually what we do is we reference a GPS signal, and that gets us even better, like microwave T2. Now this is with microwaves. So when we start using lasers, it's kind of a different story, but again, it's only in our own inadequacy. The qubit itself is perfect. Okay, so in ytterbium, what kind of made this a workhorse is this particular magic wavelength here, not magic wavelength in the sense of atoms, but sort of magic in the sense that you can buy it. So it turns out that 355 is exactly what they use for photolithography machines. And so they create these high power lasers that you can buy off the shelf, turn the key, and they turn on at 355, which happens to be a very nice wavelength for doing Raman operations on ytterbium. And so in this case, instead of having one beam for the optical qubit, you need 2 beams. Yeah. What is T1? Oh, like what does it mean? So T1 is the process where we have a spontaneous bit flip. So it flips from spin up to spin down. And T2 is the process where if I put my qubit on the x-axis, it starts to move off of that axis and rotate around the Bloch sphere in time. Okay. And so in this case, you actually need 2 lasers. So that's another difference between the 2 types of qubits. So you're doing a Raman process. The ion will absorb in one beam and emit into the other, and thereby create a spin flip. And in the case of ytterbium, this Raman light is detuned between these 2 p states in a way where we need to be far enough detuned from the p state such that we don't actually populate it into k. So that would be kind of this bad direct coupling mechanism, which depends how far detuned you are from those p states. But then we also need to be close enough that we actually drive these transitions, right? So if I just went way far away from this line, I wouldn't actually have any coherent coupling. So you have to have something that kind of meets in the middle in such a way that the bad coupling is small enough compared to the good. And it just so happens with 355 in ytterbium, this is about 10 to the minus 5, which is very good. So until our errors are down to 10 to the minus 5, we don't worry about this at all. Okay, so those are my ion examples. And let's see. Yeah, maybe let's take like a 3-minute break. So I'm seeing some like glaze over a little bit. So take a 3-minute break, stand up, drink some water, like get the blood flowing, and then I'm gonna go to the blackboard.
introducing a break in the lecture is a wonderful idea, and we should have been doing this the whole time.
Especially in the afternoon. It's tough in the afternoon. I know.
Time, on average, but also satisfies. But I think what Leo was saying. Averaging. Yeah. That's what I figured. Thank you. To do some speedy, can you do 3 different or 2 different drivings? Like this hopping in instead of in 2D, we're producing in
'Cause he was there with the fill from basically was saying and building it from the top. And we have like running driving through instances. Good night.
Still. I was thinking maybe, yeah. I was just gonna see how many people are still. Yeah, just about. Yeah. Thanks. Okay, so now I've talked kind of mechanically about how we trap the ions and what lasers, how we can use lasers to manipulate the internal states. So now what I'll do is combine this harmonic oscillator, mechanical harmonic oscillator, with this laser light that we've turned on, and we're addressing the internal states so that we can couple the two. Okay. So first, I'm going to write down, hopefully I can write big enough, the Hamiltonian in the lab frame. So in the lab frame, we have our qubit term. So omega naught is our qubit frequency. So it could be microwaves, it could be optical. And then we have our term, and I'm just going to assume we have a single mode for now in the x direction. So this is our harmonic oscillator term. And then what I also have, let's say that I turn on a laser. And I'm going to assume that I have a dipole coupling to the electric field of that light that I apply. And depending, which transition you're coupling to, it could be a dipole, it could be a quadrupole, it could be a Raman. You arrive at the same conclusions. So essentially, you're going to end up with the Rabi model no matter what, but your Rabi frequency is going to be determined by different parameters within the atom. So for simplicity, we'll just assume this is a dipole coupled interaction with the electric field that I apply. And in particular, I'll apply a laser field, which is oscillating in space and time. So it has some direction, and then it's oscillating at the laser frequency, so omega L is going to be the laser frequency. And this X position is the ion position. Okay, and let's just also assume that I have the correct polarization on this electric field so that I can couple the levels that I'm interested in. So we're not going to worry about that right now either. Okay. Then what I'm going to do is just suggestively rewrite this term as I mentioned, a Rabi frequency omega, and then sigma plus sigma minus, where these are acting on the internal energy levels. So we can think of these as like this, just the spin raising and lowering operators. Okay. Okay. So then I'm going to go to the interaction frame, and I'm going to take a rotating wave approximation. And in this case, the particular approximation I'll make is that the laser frequency and the qubit frequency are much, much larger than omega. So in the case of the ions I was talking about, right? So this omega L is generally optical. Let's say this is also optical. So these are hundreds of terahertz. And so the kind of Rabi frequencies I'm dealing with are usually max of a megahertz. So I've got plenty of room for this, taking this approximation. Okay, so then I'm in the interaction frame, and I can write down the Hamiltonian and ignore kind of these terms that are oscillating at omega L or omega naught. So I have the Hamiltonian now looks like this. It's going to be a minus sign. And there's also another term that looks like a sigma z. That is a Stark shift term. And we're going to ignore that for now because it's generally either small, or we can cancel it, or we can deal with it. It's not going to matter for what we're talking about. Okay, so let's look at this. So what we have is the Rabi frequency out front, and then we have these spin flip terms. And in this case, yeah, mu is going to be some detuning of the laser from resonance. So let's see. In the back, yeah. Oh, right, bigger. Okay, I think I got smaller as I went. Sorry, I started bigger and then got smaller. I will go bigger. Okay.
You went to rotating frame and rotating the omega naught.
Yes, I'm ignoring this now.
Then you still have, so now qubit is degenerate, but omega A dagger A, that's omega X minus omega naught.
So that's going to come in this x hat term. Wait, so I'm ignoring both. Wait. Yeah, this is going to be a constant offset. So I'm ignoring that. Yeah, we're now in this interaction picture where I only care about this term. Yeah, the coupling. In the back. Well, in this case, it's a mechanical harmonic oscillator. So these are phonons. Yeah. We're going to arrive at the same Hamiltonian. Spoiler. Right. Yeah. A relationship between the frequencies or the no, so what I buried is sort of the strength of this dipole matrix elements term. I'm calling it the Rabi frequency, and so I'm taking this dipole. Oh wait. Woo. This is wrong. Sorry. So I'm rewriting the dipole operator. Yeah, sorry about that. So I'm essentially saying I'm coupling these two levels using a dipole interaction so that I can flip the spin. And then I'm doing it with an oscillating electric field. Thank you. And then depending which line I'm using in the atom and whether I'm doing a direct qubit or a Raman qubit, this omega is going to depend on the properties of the atom that I'm particularly trying to couple the internal states. Yeah.
And are you focusing on a particular spatial mode, like a particular K that you select?
Yeah. So I'm assuming that I only kind of I'm choosing one mode of motion on the ion, and then I've directed my laser along that mode of motion.
How, in general, if the confinement is weak in the z direction, you have phonons at all wave vectors. So how do you select only a particular K? Or maybe it's spectral property.
Yeah, so I can well, so the K, right? I can choose. Let's see. So let's say I have a single ion and it's trapped like this, and this is my X direction. I can shine my laser in this direction so that my K vector looks like this. And then I'm assuming I picked the right polarization of this field to get the dipole coupling that I want.
It's okay. It's the momentum transfer from the phone.
It's essentially momentum transfer. Yes. But I'm taking a picture in which I'm still writing down the electric field as having like spanning space. So it's not like I'm saying photon in.
Classical.
Yes. So this is a semi-classical picture. So my ion is the internal energy levels of my ion are quantum, but the field is classical. I'll write bigger. I remembered. Okay.
By doing the projection of light momentum wave vector onto the x-axis.
Right. So if I wanted to couple to a different mode, say the Y mode or something, then I would send my laser in the Y direction in this direct coupling case. For Raman, you have two beams and you take the delta K. You take the difference in the two wave vectors. But essentially, it turns out the same. Yeah. Yeah, this is This is L. Yeah, in this picture, I'm saying K is exactly along that mode. But you're right that if you were off on some angle, there would be some correction. Yeah. I mean, yeah, then this just, you have to add another term here. It gets a little more complicated to write down on the blackboard, but the physics is exactly the same. Okay. Okay, so now I'm going to introduce some more terms. Okay, so eta is what I'm going to call the Lambdicki parameter, and it has to do with a relationship between the mechanical, I'm going to call this omega x. So this is the mechanical harmonic oscillator frequency and the wave vector, or the wavelength essentially of the light. And so what, if you recognize that, does anyone recognize what this expression? Yeah, the 0-point oscillation. Yeah, so this is the 0-point oscillation of the harmonic oscillator. And this is essentially 1 over the wavelength of my laser. So I'm comparing, this Lambdicki parameter is comparing the 0-point motion in this harmonic oscillator to the wavelength of the light that I'm using to address it. And so in particular, when this x naught is much, much smaller than the wavelength, then eta is small. I'm going to put 1 because it can be like 0.1 and that's still small enough. Then this is kind of the comparison that we're going to use in order to expand these exponentials and get to something that we can work with. So let me go to the next board. So you might also remember in the case of a harmonic oscillator, right, you can write down the position in terms of the creation and annihilation operators. So I'm going to use this definition in my interaction picture Hamiltonian here, as well as this eta, and just rewrite it in terms of eta. So I have omega over 2, sigma plus. I'm going to pull out this detuning term because it's just like a constant phase that I have to keep track of. And then I'm rewriting this kx term. I'm also going to assume that I set the phi of the laser to be 0. Fine. But yeah, I'm going to write this as I eta okay. And then I have the Hermitian conjugate. Sorry, I thought this went up higher. Okay. Okay, so all I've done is just done a substitution into there and expanded this out. And this is why I chose eta the way that I did. It pops right out. And now we have the time dependence on the A and A dagger in this particular interaction picture. Okay, so now if eta is small or small enough, I can expand this exponential. So I'm going to take this and I get 1 plus I eta right? Okay. So, and I could keep going in higher order eta depending on what I want to do. Okay, so what we're going to do next is look at the different terms in this expansion and what happens for each term. Okay, so let me draw a picture. So we're looking again at this like mechanical oscillator plus internal energy levels. And so we can draw this ladder of states. So this is going to be my qubit. Remember, I assumed this, or no, I didn't do that. No, I'm going to assume that this qubit frequency, oh, I need to go lower. Ladder has to start at the bottom. There we go. So this is my internal states, which have a large splitting in, hundreds of terahertz, or maybe it's megahertz. And then I have states of the mechanical oscillator, the motion, so this is going to be n equals 0. This is n equals 1. This is 0 and 1 of the internal states, and so on, right? So I can make kind of this ladder where this splitting is my qubit splitting. And then this splitting is my harmonic oscillator frequency. And so this picture of a ladder of states is going to help us understand what different things we can do. So this Hamiltonian is talking about how we couple between these different rungs of the ladder, right?
This omega x is different. The one you drew,
One.
this omega x is really not that omega x. It's omega x minus omega naught. As you drew.
No, it's omega x. The laser can be some combination of omega naught and omega x. Thought I saw a hand over there. Yeah. My omegas have a tendency to like not look like omegas by the end of the book. Sure. Is that better? Okay. Okay. So then now I'm going to play with this this tuning term here, this mu. Okay, so if I set mu to be 0, then that means I'm coupling just the internal energy levels, right? So mu up top here, let me highlight it, is the difference between the laser and the qubit. So if I set the laser to be exactly on resonance with the qubit, then I'm driving this internal energy transition directly within like a single end state, right? So this is the case where mu is 0. And so I can couple those two states directly. And then let's just take the first term of this expansion. So we're just going to take the 1. We're going to assume, or rather, sorry, we don't even have to do that, right? So the n is not changing. So these A and A daggers, they are not participating in this at all. And so what we have for the 0 case is just some coupling for the same n. And there are some higher order terms. So if toward them, this omega n would just be omega. But I'm going to go ahead and include at least one of them. So if I went further in this, then I would get a 1 minus, I would have an eta squared term, which has an n attached to it. I'm not going to go through the second order term, but just trust me. Okay, so like I said, if eta is small enough, this is very, very small, and this omega is essentially the Beer-Rabi frequency. However, if eta isn't small enough, or if n gets very, very large, it starts to affect this Rabi frequency. Mm-hmm. No, I've said nothing about the relationship between omega x and big omega. Right. No, so I was saying that this changes the phonon number by 1, and I'm not changing the phonon number in this carrier term. I'm looking for the transition where the n stays the same.
Is that comes from second order in eta?
Yeah, so if I kept going, then yeah.
Then say the A, you get A dagger.
Mm-hmm. Okay. Okay, but if eta is small enough and n is small enough, I can ignore that. And then this Hamiltonian is just a, your typical Rabi model. So H, actually, I'm going to go right on the other board. This is like too low for me. Okay. Okay, so this is still the mu equals 0 case. And let's say that eta is small and n is small. Then H is just 1/2 omega. And I'm going to say that this is sigma beta. And let me just define that. So if sigma theta is defined as some combination like this, minus I theta plus I theta. So I have a combination of sigma plus and sigma minus, or just written another way, in the polys, this is sigma x cosine theta plus sigma y sine theta. And then I can, in this case I said, we have this phi parameter that I said, oh, we're just going to make the laser phase 0, but you could make it whatever you wanted. And then this beta is essentially is this phase of the laser. So depending on the laser phase that I choose, this could be just a sigma z, or rather, sorry, sigma x, like usual, but I could also do anything in the XY plane just by choosing the phase of my laser. Okay. Yeah, I kind of dropped the phi, but it hangs out everywhere. Yeah, so if you follow it more carefully, you'll see that you can tune this angle from sigma x to sigma y and anything in between. Yeah. These down here, they're split by omega x. So the same splitting as these upper ones. So that's why it kind of goes up a little bit every time. Maybe I should draw that on this board, like really big. It's hard to see on the bottom of that bottom board, huh? Okay. Yeah, because I'm going to use it again right now. Okay. So this is just my internal 0, and I'm walking up in n. And then similarly, I have the one states walking up here. So this splitting here or here is the mechanical omega x, and this splitting is omega naught. Okay, so now if I tune my laser to be where the detuning mu, so this mu, remember, is this difference between the laser and the qubit. If I tune it to be about omega x, we call this a blue sideband because it's blue detuned from omega naught, right? I've increased the frequency just a little bit by omega x. And if you plug that into our Hamiltonian for mu, so this is the blue sideband, then what you get for the Hamiltonian is you have some coupling between n+1 and n levels, right? So with this coupling, I've increased the n value in addition to flipping the spin. And then I have sigma plus a dagger minus sigma minus a. So my change in n is +1. And then if you try like applying this Hamiltonian, you can figure out how this modifies the Bayer-Rabi frequency. And so you can write down this expression for this is just going to be eta square root n+1 times the Bayer. Oh my gosh, my omegas get worse over time. I'm sorry. Times the Bayer-Rabi frequency omega. And that was worse. Okay. Mm-hmm. Here. Yeah, so if you yeah, wait, so what's the question?
There's already a dagger.
Mhm.
There are another outside of
Yes. Okay, so this is the blue sideband, which from the perspective of kind of cavity QED is what we call the anti-Jaynes Cummings Hamiltonian. It's weird. We have simultaneous spin, flip, and phonon creation. So we excite the qubit and create a phonon with one operation, or the opposite, right? So normally you would think of it, well, let's do the other one, right? So the other case is what we call the red sideband. And in this case, the Hamiltonian is just the Jaynes Cummings Hamiltonian, where in this case we're tuned minus omega x, so would be like going down the ladder. Minus omega x. So this is maybe what's more familiar. You have annihilate a phonon and create a spin excitation. So this is maybe the more natural when you have a cavity that's like holding your photons. But you know, the key difference here, right? So this omega x is smaller than this omega naught. They're not close to each other. So I can actually just do this. Whereas when you have a qubit and a cavity that are close to resonance, this would go away in your rotating wave approximation. You would assume that these oscillate very, very quickly and they go away, right? So just to be explicit, right? So you have terms that are like omega x plus omega naught, and then you have terms that are the the difference. Easier to write the other way, but that's okay. And so if these are close to each other, then you would assume these terms go away. And that's what happens in cavity QED, but we don't have that. We can keep these terms. And so we can actually do these blue sideband operations. And then in the case of the red sideband, this is what we use for sideband cooling. So just to touch on that briefly, right? So let's say I have, 3 phonons. I can turn on my red sideband, which removes 1 phonon, and then use my repumper and make this guy decay down to the ground state. Can do this again, decay down to the ground state, and do this over and over until I have 0 phonons left. So that's how we do sideband cooling. Let's see. And then these will be the only terms that we need in order to do our 2-qubit gates as well, which is what I'll talk about next time. So essentially, right, actually, let me just go to one slide. Right, so these are the red and blue sideband terms I was just talking about. And then if I turn them both on at once in a very hand-wavy way, and we'll be more rigorous about this next time, then I get, right? So now I'm turning on both blue and red at the same time. Then if I expand all of these, and again, wave my hands a little bit, what I have is a sigma X term, and then an A dagger plus A, which is X. So I have a sigma X coupled to an X, which is spin coupled directly to motion. And this is going to depend on your spin state, right? The sigma X. And so this is how we create a spin dependent force, which creates entanglement between spin and motion. And that will be what we use for our gate. Okay, I'm going to stop there, but I can take questions.
This pressure, so we got depend on, you think that this principle can create
Yes.
problem in fact.
No. So okay. So the question's about this N creating decoherence, and that's what this is showing. So, this is carrier Rabi flopping. So this is just looking at applying this particular term and looking at the 0 and 1 state in the ion. And so as my ion gets hotter, these flops slow down, and so that would create an error if you're trying to do like a particular rotation. However, with sideband cooling, we're down below 1 phonon usually. So this is a very, very small error. And then in addition, eta is small. So say eta is about 0.1. So you get 100-fold suppression there, and then N is also less than 1 phonon. So this is very, very small. And we also have ways of correcting for things like that anyway with our pulse sequences. So it really just is a non-issue when we're doing quantum computation. What is cool about this effect, though, is you can use it as like a thermometer, right? So I can measure what my excitation actually is. And if you assume you're in a thermal state, what this looks like is a decay. And so this would look like decoherence. So in this example, this is like a miscalibration. My Rabi frequency is slower than I thought. But when I take an ensemble average in a thermal state, what I actually get is a envelope. But again, if you're cold enough, you don't see this at all. But you can use it for thermometry to figure out what your ion like phonon occupation is. Mm-hmm.
This is for one ion?
Yes, I've assumed just for now 1 ion. Next time we'll do many ions. Yeah. Good question. Okay, so the lifetime of the phonon modes. So lifetime's kind of an odd way of putting it. So it's different from photons in that we don't lose phonons. There's no mechanism whereby we lose phonons, but we can gain phonons from heating. So that's kind of a lifetime. So we can, but we can get heating rates very, very low for the modes that we care about. Let's say that goes away. But we also have motional coherence time. So essentially like emotional T2. And that can be like tens of milliseconds, let's say. Like what, how do you characterize it or what? No, so you essentially can create like superposition of Fock states and then use the decoherence of those superpositions to measure your motional coherence. Yeah, kind of in the same way you would with like a cavity or something, but it comes into play in an indirect way, right? So I just mentioned at the end, we're going to make this like spin motion entanglement in order to create spin-spin entanglement. And so your motional coherence time is only relevant in so long as you're creating the spin motion entanglement. Otherwise, the spin does not care at all, unless you couple it. Mm-hmm. Yeah. Yes.
This is going to let us plug gates. This is the idea. Okay. Great.
Yeah. So this is single ion because that gets you exactly the Hamiltonian that you need. And next time we'll add more ions, but essentially is the same thing, but like you have to keep track of more indices. There's going to be more ions and more modes to contend with. But the principle is basically you turn on red and blue at the same time, and you can couple spin and motion for multiple ions. Yeah. In the back. Well, okay, so I shouldn't be glib. Okay. So they were doing C0 gates and ions in 1996. And when was the first like Rydberg entangling gate? Is in the last decade, right? So ions have just been at this a lot longer. That's all I'll say. Thank you.